All right, guys, so now we're going to move on to the kind of the connection between exponential and logarithmic expressions. So they give you, if a of x is equal to y, then log a of y is equal to x. This just means that these parts are interchangeable. If you have a base a in an exponential, it will be your base of a in your logarithm. Your exponent becomes your answer, and your y, of course, is your log a of y. So each part of these expressions coincide with each other. So we can actually rewrite an exponential equation as a logarithm. So again, we're going to go about practicing it. So notice I'm not telling you to solve. I'm not telling you to find 2 to the power of x. You're not solving for x. Right now, we are purely working on rewriting. We will get to the point where we are solving. We're just not there yet. So, rewriting, I have 2 to the power of x equals 726. Right, so I'm going to write it. So first thing, log. I need my base is going to be base 2 of my answer, which is 726. So log base 2 of 726 is equal to my exponent of x. Okay, we have 3 to the power of x equals 81. I have a log base 3 of 81 equals my exponent x. Now, anytime we're working with fractions, I like to tend to use parentheses whenever I'm rewriting. You don't have to, I just like to. We have our log base of 2 of 1 over 32 equals my exponent of x. Okay. Oops, sorry, I went up too high. Well, now we have log, well, we have 1/5 to the power of x equals 625. So again, log base of 1/5. Now this is where it gets a little complicated, but so log of 1/5. Remember, I'm making sure that that looks like it is a base of 1/5. You can write it as 1 over 5. You can do it with a slanted slash or anything like that. Just as long as everything is in the right spot and you're not, please, please, please do not do log 1/5. This is wrong. This is wrong. I will count it wrong. You need to make sure that these problems, these fractions, look like exponents or they look like they are bases. Do not make them look like they are just big numbers part of the equation, because they are not. So log 1/5 of 625 is equal to my exponent x. Now we have a log base of 10. Remember, this is usually like an understood 10, so technically we don't have to put it because we know it's an understood 10, but you can put log 10 of, in this case, 10,000 equals my exponent, x. So again, this is the same as saying log of 10,000 is equal to my exponent. These two things are the same. Just please know that if there's no log with a base, or sorry, if there is no base with that log, it is an understood 10. Now, oh, this one's different. We have an e raised to the power of x. Well, e, the opposite of e is going to be our natural logarithm. So whenever I go to rewrite this, I will actually have ln of 178 is still equal to my exponent of x. Okay, so e, just make it an ln of my number equals my exponent. Okay, now we're going to talk about changing the logarithm back to the exponential form. And I like to use what has been dubbed by my students in the past, the circle method. I don't know if anybody else calls it that. That's what we call it, circle method. It's just a little way to help you remember exactly how to put it back as an exponential. So I'll show you how it works. We say we have a base 7 raised to the power of 3 equals x. So I go 7 raised to the power of 3 equals x. Again, I have my log base 1/3. So I do 1/3 raised to the power of 5 equals x. So 1/3, put it in my parentheses, raised to the power of 5 equals x. Notice I did not say solve. I'm just rewriting. I'm changing the logarithm expression. So 6 raised to the 1/2 is equal to x. So 6 raised to the power of 1/2 equals x. Please, again, it's not 6 1/2. That is incorrect. I will count it wrong. You will get it counted wrong on tests. They are not the same. So this is not the same as this. Got it, guys? Okay, so 3 raised to the power of 1/4 equals x. So 3 raised to the power of -4 equals x. This one, we are missing our log. And remember, like we said before, if there is no log there, or if there is no base there, it's an understood 10. So we'll say 10 raised to the power of 4 equals x. 10 raised to the power of 4 equals x. All right, ln, right? We use e. So we say e raised to the power of 9 equals x. So we'll say e raised to the power of 9 equals x. Let's see. Now we're going to look at some additional... Oh, hang on, guys. My computer's slowing down. We're going to look at tables and how to do logarithmic functions in our graph. But here's the thing. We're doing it different. You know how normally I would tell you if we're going to graph, okay, we're going to do, we're going to put 0, -1, -2, 1, 2. Well, this is actually the opposite. Instead of putting them in x, we're actually going to put them in y. So we're going to say 1, -1, -2, 1, 2. And we're going to solve for x. So we're going to take our logarithm, log base 2 of x equals my -2. And now I'm going to use my circle method. I'm going to say 2 raised to the power of -2 equals x, and I'm going to solve. What is 2 raised to the power of -2? Well, that is, the negative makes it flip, and the 2 squares it, so it'll be 1/4. So I will have a point at 1/4 -2. When we're dealing with logarithms, we actually input the y and solve for the x. It's very important. You have to change the method for logarithms. Now we're going to do -1. So we have a log of 2 of x equals -1. So 2 raised to the power of -1 equals x. Well, that negative means I'm going to flip it, so it's 1/2. And I will plot my point at 1/2 -1. Again, I do log 2 of x equals 0. So 2 raised to the power of 0 equals x. 2 raised to the power of 0 equals x. Which of course is 1. Anything raised to the power of 0 is 1. So I will get 1, 0, log 2, x equals 1, Well, that's 2 raised to the power of 1 equals x. Well, that's just 2. So my answer is at 2, 1. Log 2 of x equals 2. So that means 2 raised to the power of 2 equals x, which is 2 squared, which is 4. So I have a point at 4, 2. Now you're going to see how a logarithm looks different from an exponential. So we're going to plot some of our points. I have my first point is at 1/4. So 1/4 down 2. So 1/4 down 2. So somewhere right here. Again, I try to get it as close as I can. It's not perfect. All right, and then I have 1/2 -1. So right here. And then I have a 1, 0. And then I have a 2, 1. And a 4, 2. Now notice I'm getting very close to the y-axis this time. So I'm actually going to go along the y-axis. And I'm going to finish graphing. And if I needed to, well, no, we'll just keep going. It looks like this. All right, and because from left to right, I went from negative to positive, this is actually an exponential, well, a logarithmic growth, actually. So this is a growth formula. The way we do our domain and range for these is different. Our domain, remember, we're reading from left to right. Our domain, it looks like it's never going to pass that y-axis, so I know it's going to go from 0 to positive infinity in this case for the domain. And the range is actually going to be from negative infinity to positive infinity. So for logarithms, our boundaries are flip-flopped. So our domain is different. Our range is negative infinity to positive infinity. All right, let's do one more. Remember, logarithm, we're actually going to go 0, -1, -2, 1, 2. We're going to input them and solve to find x. So we have a log 1/2, log base 1/2 of x equals -2. So it's 1/2 raised to the power of -2 equals x. If I were to, the negative flips it and the 2 squares it, so it's actually just going to be a 4. So we have a 4, -2. Now we have a log base 1/2 of x equals -1. So 1/2 raised to the power of -1 equals x. The negative flips the fraction to make it a 2, and the 1 doesn't do anything to it, so it's just a 2. So it's an answer of 2, -1. Again, log 1/2 of x equals 0. That's 1/2 raised to the power of 0 is equal to x. Well, anything raised to the power of 0 is 1, so I have a point at 1, 0. Again, do my log 1/2 x equals 1. So that's 1/2 raised to the power of 1 equals x, which I solve and get just 1/2. The 1 does not do anything to it. So I have a point at 1/2. Oops. 1/2, 1. And then log base 1/2 of x equals 2. So that's 1/2 squared equals x. Well, 1/2 squared, 1 squared is 1, 2 squared is 4. So that is 1/4. So I have a point at 1/4, 1. Okay, now I have to plot it. I have a positive 4 down 2. Positive 2 down 1. 1, 0. So I have a point here. And then I am going to plot my next point, which is 1/2, 1. And then 1/4, 2. Oops, there you go. That's a 2 that I plugged in. Okay, so a 1/4, 2. So I'm gonna have a point here. Now notice I'm getting really close to the x-axis, but it's going down. So it's going from positive infinity and it's decreasing, and it'll just keep going. But I will have a vertical asymptote of 0, which will affect my domain or my x values. So so this is actually a decay formula. Remember, from left to right, it's going down. So this is a decay. And if I were to do my domain, remember, domain is influenced by that vertical asymptote. So it would go from 0 to infinity. And my range, well, it keeps going from negative infinity to positive infinity, from bottom to the top. All right, if you have any